slides again. If I can find out where I need to be. Oh, they're fun. They are fun. I enjoy notes. All right. So the end of last week was pretty much a review of what we talked about in chapter 5. Today, the last section that we're going to be covering today and tomorrow is going to be discussing trends. Okay, what's a trend? Something that's done by a lot of people, or also commonalities. Trends are patterns, if you will. Okay, and so we're going to take a look at a few select patterns. We're going to call them trends that are in the periodic table that aren't told to you on the surface of the print. Okay, there's a lot of underlying information that is there within the table itself. Okay, and so when you start investigating and looking into trends, you can then begin to make predictions about the elements, okay, and about characteristics. So even I teach an entire chapter in my honors class just on the trends themselves. We get a lot deeper than we do in here, but it is a valuable thing to know if you plan on, dealing with the periodic table, even if it's just for a test. Knowing trends can help you solve answers. But our first trend we're going to investigate today is the atomic radius. Now, if you remember, a chapter or so ago, we talked about the electron cloud. Again, it's that newest model of an atom that is based on the probability of where the electron of the atom may be and does not have a clearly defined edge. So it's kind of just looks like a beehive. Okay, beehive being the nucleus, and all the little bees around there just buzzing around there are like the electrons. Okay, they don't really have a set location, but they're just all around there. And so that's what we refer to as the electron cloud. And that fits into the atomic radius. Okay, the atomic radius is simply how closely an atom lies to a neighboring atom. Okay, if we measure from the nucleus to the outer edge of that electron cloud, that's the atomic radius. Okay, so for most metals, the atomic radius is half the distance between adjacent nuclei in the crystal of an element. That's fancy talk. Okay, that's fancy talk. It's just saying, if you were to take two atomic neighbors, and measure the distance between their nuclei, half that distance is their atomic radius. For most nonmetals, the atomic radius is defined as half the distance between nuclei of identical atoms that are chemically bonded together. Sure. So, atomic size is a periodic trend that is going to be influenced heavily by those electron configurations. And Caden, after we get through these, I'll go back at the very end and you can get caught up, okay? So let's look at the trends. So let's start talking about the trend of atomic radius within a period. So again, we're looking at the horizontal portion of the periodic table. As we go, and you should be able to see this on your notes, as we go from left side of the periodic table to the right side of the periodic table, there is a general decrease in the atomic radius from left to right. So meaning, as you go left to right, the size of an atom is becoming smaller. And this is why. As we move from left to right, we have an increasing positive charge in the nucleus. Or to put that plainly, we're adding more electrons. We're adding a single electron every time we go further to the right. And as you stay in the period, the principal energy level remains the same. As one proton is added, you have one electron added to the same principal energy level. But then this is where the idea of valence electrons come into play. We've talked about valence electrons quite a bit. We've also talked about another notion that hasn't really been named yet, and that is the idea of core, C-O-R-E, electrons. Okay? Core electrons are all of the electrons within an atom that are not valence electrons. So basically all the atoms not on the outermost energy level in the s and p orbitals. All the rest are considered core electrons, but no digits. Okay? Those core electrons stand between the nucleus and the valence electrons. They're kind of like the army or a military group that is helping to shield or block the protons from attracting the valence electrons. But as we go from left to right, we're adding more and more protons to that nucleus. But the number of core electrons are remaining the same. So those core military electrons, they're not changing size, they're staying the same. Meanwhile, we could say the protons are the enemy, they're increasing. And as you get to have more of an increase in the protons, they're charged. Their pull on those valence electrons is going to be increasing every time we go from the left to the right. And so, increasing that charge, that overall charge, and increasing the attraction, those core electrons just don't stand a chance to those added protons. And so, you start to see those protons pull on those valence electrons more and more, and you start to see it shrink. Okay? Now let's talk about the vertical component, the group component of the atomic radius trend. As you go from top to bottom, you have a general increase as we go down a group. So that means the size of an atom increases. And this is because as you go from top to bottom, you are increasing your energy levels, and your outermost orbital size is also going to increase, which places your valence or your outer electrons further and further away from the nucleus. It's very similar to if you took a South Pole magnet and a North Pole magnet, and you move them farther away, their attraction to each other is going to be minimalized. So the farther they get away, the less pull the protons are going to have on those valence electrons. And so you're going to see the result being in atoms becoming larger as you move further downward. So those are the trends of atomic radius of neutral, normal atoms. But what happens when we start taking a look at ions? Again, ions are atoms that have either had electrons removed from them, so they have a positive charge, or electrons added to them to where they have a negative charge. So when you lose electrons, this causes atoms to form positively charged ions, and positively charged ions are going to become smaller than their neutral version of the atom. And that is because you begin to have, when you remove the outer electrons, you now have emptied out your outermost orbital. So you've now decreased the size by losing electrons. And that also plays a part is there is an electrostatic repulsion, meaning all of the electrons in there, they don't like to be near each other because they're all negatively charged. So, those with like charges don't like to be near each other. But as you begin to remove electrons, and at the same time you're maintaining the number of protons, that just even gives you the protons a stronger grip on the electrons. The electrons are outnumbered. So you're losing an outer shell, and you've got more protons that can pull in the electrons even closer. So that is why positively charged ions are smaller than their neutral version. Then if we look at a sodium atom and a sodium ion, the sodium atom, its atomic radius is 186 picometers. If we look at a sodium ion, where we removed one electron, the only valence electron that sodium has, it now has an atomic radius of 95 picometers. So it almost was reduced by half by only losing one electron. But gaining electrons cause the atom to form negatively charged ions, and negatively charged ions are going to become larger than their neutral form. This is caused by a few things. When you add more electrons, you are actually going to increase that electrostatic repulsion that I mentioned, which again is going to then cause electrons to move even further apart. And so when you do this, you increase your distance from the nucleus. The protons aren't going to be able to have as much effect on you because now the electrons are actually going to outnumber the protons. And so chlorine, which is a non-metal, non-metals are going to form these negatively charged ions, whereas metals form the positively charged ions. A neutral chlorine atom has an atomic radius of 100 picometers, whereas the chlorine ion, by just simply adding one electron, has an atomic radius of 141 picometers. So let's talk about trends both horizontally and vertically when it comes to ionic radius. Okay. So for positive ions, which is against, the left and middle portion of the periodic table, all the way to this group right here, group 13. The ionic radii are going to generally decrease left to right. So as you go from group 1, move it over to group 13, they become smaller. So it follows a similar trend to the neutral atomic radius trend that we first talked about, but that's only to group 13 for ions. For negative ions, essentially those from right about here, right there, the ionic radii are going to decrease from left to right. So there's kind of a split here. When we get for groups 1 through 13, they become smaller. When we get here, they increase again when they become negative, and then slowly decrease again. You should be able to see this in your notes as well. It shows you where that split is on the periodic table. Vertically speaking, so within groups, positive ions, again, are going to increase in size. So are negative ions. So again, going top to bottom, for both positive and negative ions, they're going to increase in size. And again, this is all going back to what's occurring is they are increasing the number of principal energy levels, and therefore they are increasing their overall distance from the nucleus. So far we've discussed atomic radius and ionic radius trends within a periodic table. Okay. By looking at that, we could predict, let's look at magnesium and calcium. Okay, right here. Magnesium and calcium. Who would have a larger atomic radius? Magnesium or calcium? Who would have a larger atomic radius? Just neutral atom atomic radius. What do you think? Bailey? Okay, John says magnesium. Who magnesium, calcium, who would have a larger atomic radius? Now you didn't say that with a whole lot of what's the word I'm thinking of? Confidence. Thank you. Conviction. Yes. Well, we discussed. You notice that these are in the same group, right? So the trend for atomic radius as we go down a group, it increases. The size increases. But since calcium is below magnesium, you were right. Calcium should be larger. Now let's talk about here, rubidium and strontium. They in the same group or same period? What's that? No. What'd you say? You say rubidium? You agree with them? Who agrees with Caden that it's rubidium? You should agree with him. Because in a period, we decrease as we go to the right. So since rubidium is to the left of strontium, we should expect rubidium to be larger in terms of atomic radius than strontium. So we made predictions, which they are true. Just simply using those two bits of information didn't measure anything. Okay, we simply used the trends. And now we can obviously get much more complicated questions with that, but not today. So let me stop the recording. Those of you at home, we are done for the day. So thank you.